Now I have the friend. Sorted. There. Okay, good morning, everyone. Welcome to the third day of this SIMPA school. And this day starts with the second lecture of Sara. So, Sara is continuing to what she started yesterday. And I can see that there are lots of interest of the participants in the theory she is introducing. So, over to you, Sara.
Thank you. So we started with the definition and some stuff that we need. And just to warm up, I want to use once more time this restriction lemma. We will see. But before that, I need to recall what is the definition of a subgraph. When I have a graph like G and with vertices VG and edges EG, and I take a subset of vertices, then and a subset of edges, then I will have a new graph which is called a subgraph. So this is very natural. But then I call this subgraph an induced one whenever for any two vertices inside this subset, the connection that we have in H is the same as what we have in G. So, for example, here in this graph, if this is G, then this is a subgraph because it's just consists of a subset of vertices and a subset of edges. But this is not induced because on these two vertices, if I take them as I and J in this subset, I have a connection here, which I'm losing it here, right? So this is not induced. However, it is a subgraph, but this graph is a subgraph and it is induced because for each two vertices here, I see the same connection in G. So here I have this one, here I have this one, and there is no other vertices that I should concern about, right? So this is then induced. And we are interested in induced subgraphs because we can have some control on them. Subgraphs in general are not that much interesting for us. So is it clear to everybody what is an induced subgraph? Okay. And if our subgraph is a matching in G, you remember from yesterday that a matching in a graph is a bunch of edges which do not share any vertices. If our subgraph H is a matching and an induced subgraph, so it means that there is no such connections between them. So it is induced. Then we call this an induced matching of G. So going back to this example, here I see a matching a two matching, but is it also an induced matching or not? No, because there are some other connections. So this is not induced. The biggest induced matching in this graph has how many edges? Just one, right? So this is an induced matching and I cannot extend it, right? So it shows to us that the maximum number of induced edges in an induced matching can differ from the matching number. But we also put a name for this. So the maximum number in an induced matching is denoted by nu1 of G. I mean, there are different notations for this, but I use this one. Number of edges just to make it more precise. So for this graph, nu is 2, but nu1 is okay. And now let's go to the ideals. Suppose I have an induced subgraph. So I have G, I have an induced subgraph of it. So for each of them, I have their edge ideal. And I can take their square free powers. And each of them has their own minimal graded Fourier solutions, okay? And now if I know that this is the minimal multigraded free resolution of G, and I'm interested in finding the multigraded minimal Fourier resolution of this one. And yesterday we saw a tool that sometimes it helps. That if I have a resolution for a bigger structure, I can somehow restrict myself to the smaller situation and get a multigraded Fourier resolution in that case. Yeah. So if you remember, just a very short review, that we had a monomial ideal, its minimal graded Fourier resolution, a monomial given, right? And then we took this ideal and we could restrict our resolution to find a minimal graded Fourier solution for this. And the key is this. And in one case, we saw that we can take this, the everywhere one vector, to get the square free power out of ordinary power. But here, just to achieve the resolution of this one, what is the candidate of M here? And yesterday we saw that there is a correspondence between 0, 1 vectors and monomials. So you can give me a vector here, somehow describe.
Product of the variables that are appearing in the vertices of H.
In the vertices of H. So to say xi1, xi2 to xit, let's say, where V of H is just these indices. right? So if we restrict ourselves in the to the vertices of H or the variables appearing there, then we can say that, okay, this is the same as this. Okay, you can observe it if you have some doubts right now later. And so what it means that I can compare the invariance, the algebraic invariance that I'm interested in for G and H. So it means that, just to recall the notation, the graded Bethe numbers of square free powers of H are behind the ones for G. The same happens for the projective dimension and regularity. Yeah, and we may use this one today. Okay, so this was another use for this restriction lemma for any induced subgraph. And in particular, when we want to work with induced matchings, we can benefit from this, and we will see how. Okay, but now I told you that one of the motivations to go to this direction was studying powers, the ordinary powers. And I want just to recall a result there, that regularity of the ordinary power for edge ideals is bounded below by 2k plus nu1. Now we know what is nu1 minus 1, and above by 2k plus nu. Yesterday we saw what is nu, the matching number, minus 1. And this is due to Banerjee, Yarslan, and Taiha. It's a combination of results of 2015 and 2020. This is for any k here. That's
What is new one of G?
sorry, nu1 we just mentioned here that it is the induced matching number, the maximum number of edges that you can put in an induced matching, a matching which is an induced subgraph, right? Okay, so then when we work with the square free powers, we are somehow tempted to see how can these two vary to give us some bounds, lower and upper bounds for these square free powers, okay? And for the lower bound, so let G be a graph, a simple graph as before. Regularity of the square free power, the case of square free power, is bigger than or equal to 2k plus nu1 minus k. I mean, you might say why you don't write nu1 plus k just simply. I mean, I like it more just because it is more similar to this, and we can see exactly what is the difference. So here we are subtracting 2k plus nu1 by 1, but here by k, okay? So, and it's clear that when k is equal to 1, these two lower bounds coincide. But for a bigger case, of course, this is a smaller number. So we don't prove it in all details, but I would like to give you a sketch. We begin together, and I would like to give you for some hints for certain cases, and I will ask you to just, if you wish, to complete the proof at the end. So, I mean, my goal is not to go through all details, but I would like you to have at the end some ideas of which kind of results exist in this direction. And also you have some tools to look at the problems, and at least you can read the papers after these lectures, hopefully more easily. Okay, so
Is it class K or everyone?
yeah, this is K, and as I said, this is exactly nu1 plus K. You can see it as this, but because I just would like to compare it more directly with this one, I prefer this way of writing. Yeah, but this is K. Yeah.
So
Okay.
nothing is simplified to K minus K.
Sorry. Yeah, as I said, I would like to have this in mind always, that they are very similar, but here we are subtracting by 1, but here by K. But yeah, this is the real bound. Okay. So, and as a sketch of the proof, okay, I don't want to write all the time this nu1. I denote it by R in this proof at least. So when nu1 is R, so the induced matching number is R, it means that we have an induced matching of size R in our graph. Okay, so let us fix that one. Let H be an induced matching of size R. For sure exists. And when it is an induced matching, it is an induced subgraph. So I know how its resolution is related with the resolution of IGK, right? So here we just summarized that the regularity of any induced subgraph is bounded above by the regularity of the square free power of the graph itself, right? And now I'm searching for a lower bound for this. So if I can put this bound here, 2k plus r minus k here, if we can put it here, then we are done. Agree? So if I can show that the regularity of k the square free power of h here is this induced matching, is bigger than or equal to this number, so this will be a lower bound for the regularity that I want. Agree? Okay, so this is the goal. But we recall what was the regularity. Regularity was the maximum of j minus i's, where beta ij of the ideal, I don't write ideal, just to simplify the notation, is non-zero. So now we should claim that there is a Betti number, a desired Betti number with right indices, which provide this bound for the regularity. So now we can just claim that so it is enough to show that beta r minus k and 2r of k squared to the power of h is non-zero. Okay. Now let us start to read from here. If one shows that this certain beta number is non-zero, what is the difference between the two indices that we are interested in? 2r minus r plus k, which is r plus k, right? So this is exactly the same thing that we want here, yeah? But in the definition of regularity, we have the maximum. So if we say that this is non-zero, this is one of the candidates that can give the regularity to us, right? But the maximum is regularity. Maybe this is not the maximum. So that's why we say that this regularity is bigger than or equal to this number. So the strategy is clear to everybody. With the definition of regularity, we are searching for maximum of such integers, which gives us non-zero beta numbers. And we say that if we show this beta number is non-zero, then the difference of the indices would be an element in this set, and the maximum would give us the exact value of regularity. But here we can have just a bound. Okay, but then we should know much more about this to show that the beta number is really non-zero. So for example, if I put this k to be nu1 or r, I just want to show you specific cases that's how we can deduce this non-vanishingness of the beta numbers. So if k is equal to r, the induced matching number, okay, what would be the ideal itself? What are the generators of this ideal? But I may have a different induced matchings. So how many generators then this would have? Okay, in a maximum induced matching of H, right? And H was itself an induced matching, yeah? So it was just a bunch of edges which produced a induced matching, right? So this is just now, so suppose E1 to ER was my induced matching providing H. And now here, what I have is just X E1, X ER, right? and that's all. But maybe I did not use this before, but I think you saw it in the other lectures. It is the product of x's, and you have just 0 and 1 if it appears in E1 or okay, but then this is just a principal idea, yeah? And if we want to write its resolution, we just mentioned yesterday that I have this, and it has only one generator, so I have S1 here. But if I want to manage the degree, I should put something with our notation yesterday here. What is the degree of this element here now? I have R guys in the product. Sorry, 2R, and each is of degree 2 because they come from edges. For example, this is x1, x2, the other one is ixj, and something like this, right? But the total degree is 2R. Right? And this means that I'm taking a standard basis here, just 1 of degree 2R, and take it to this element. So this goes to xe1 to xer, and the kernel of this map is what? It is just 0. Because if you, I mean, the elements here are multiplication of this, the only basis element, yeah? And then the image is just given by the only element here. And of course, when it goes to 0, it means that the element itself was 0. So this is a very simple Fourier solution, graded 1 for this ideal. And here, let us read this Betti number. What is this Betti number now? This is the 0th homological degree, right? So this is beta 0. And what should I write here? Always we write the homological degree, the step, the number of a step, and then the degree. So I should write 2R. Agree? And this is 1, so it is non-zero. But it is the same as the one that we wanted here. Since R and K are the same, so at least in this case, when K is equal to R, we are done. Agree? Or another special case, when K is just equal to 1. When K is equal to 1, it means that I am working with the ideal itself, the first square free power. And then you know that since H was an induced matching, it is generated by xe1 to xer. And what is special with these generators, how they are related? When this is an induced matching, these edges are disjoint. Agree? So You might know that such ideals are resolved by causal complex, and if you do not know, you can just keep in mind this keyword. It has a very nice construction, and you can build the resolution of these types of ideals very easily. At least you can read them numerically and in a very nice combinatorial way. So, and if I just want to give you some ideas how you can read them at the end, so in each step, I don't want to go to the details. I don't want to talk about the exterior algebra. I just want to give you a combinatorial intuition. That's how they look like. So for each step, like F0, the bases correspond to each generator, of course, as always. So each of them plays a role. Okay. I mean, it's better to write it for the quotient, and F0 would be then the ring itself. And then for from the first step on, you have the elements themselves. The next step, the basis would be given by combination of any two pairs. And here, there is no difference for us between EIJ or EJI. So, and don't worry about this notation for the moment. I just want to tell you that the Betty numbers here is just the R choose 1. Here is R choose 2. And then if you go further, in the last, since we have R here, the basis corresponds to E1, ER, and the Betty number would be given by R choose R. Okay, so I just want you have such an intuition, then later you can see the algebraic definition precisely. That's what the causal complex is. But I don't want to go to the maps, the whole construction. I'm just interested in the numeric point of view and these Betty numbers. Okay. And here I moved, I mean, somehow I shifted the indices. Maybe I need to make a comment here that what I told you yesterday for the resolution was just for the ideal. So we started from the ideal, we built it. And now if I want to make a resolution for the quotient of I, you will have R itself here. So it will be F0. And from here on, you get the same as ideal. Okay, so we wrote this for this ideal. But if I want to write it for the quotient, then it would be S mod I, S, and then what I have here, S minus 2R, 0. So somehow you add this part in the beginning of your resolution and you shift the indices by 1. You can later see why this has the properties that we mentioned yesterday. But this is always the case that we sometimes need to move from the ideal itself to the quotient and vice versa. And it means that when I'm talking about the Betty numbers of the quotient, when I say beta I and J, it means that I'm talking about beta. Okay, I shifted to the left, right? So if I'm talking about the ith step here, it means that I'm talking about I minus 1 steps here, right? And now if I go to this case that we were just discussing for k equal to 1, let us put it here. We were interested in this one. So now with 1, we have r minus 1, yeah, and 2r. So let us read this Betty number here. I'm talking about the ideal, and with this remark that I made here, it will be beta r and 2r for the quotient. Because when you think about the causal complex, it's better to consider the quotient. And what is this Betty number? It happened at the end. So we are having it here, and I said that this is the Betty number. You can see it, you can check it later, but it's not trivial actually. And I told you that this is the basis element that gives this Betty number to us. And in grading such a resolution, we consider in the very first step, we put degree 2 for each of them because they correspond to the edges. And now I have a pack of R of those degree 2 elements. So I read it as a 2R degree element. So it is R choose R, which is 1, and anyhow it is non-zero. Okay, so for R, k equal to 1, for k equal to R, which was the same as nu1 of G, we at least we provided such a non-zero Betty number. And we said that having that, we can have this question mark checked. And then we get our lower bound for those cases. Still, there are cases remaining, but I just wanted to show you that you need to understand the generators. In a very small k, it was just the edges. At the end, for a very big k, it is a principal ideal. It is bunch of all edges. It is just the whole induced matching. And in between, the generators are coming from a part of our induced matching, right? For k equal 2, you are combining each 2 elements of your induced matching. For the 3 power, you are combining the 3 elements. And having in mind the combinatorial structure, you can think about how you can find the resolution. For those who know about resolutions and some combinatorial algebra, it might recall some known structures, but for those who are not that much familiar, maybe they should try to create some tools or read more. So this is not an, I mean, I'm giving you also this as an exercise, but this is an advanced exercise now. This is not an exercise for the beginners in this direction, just to complete the gap. What describe the generators and also the resolution for k equal to 2 to nu1 minus 1. Okay, so this is our remaining case. You can think about it. But here, I forgot to put this. It is for any k between 1 and nu1. And already here, a research problem. I mean, from nu1 is not necessarily, we had an example, equal to nu, so it can be strict. So now there's a gap here. We know from 1 to nu1, what happens? We have a nice lower bound, which generalizes somehow the case of ordinary powers, but there is a gap afterwards. What happens in between? Do we have the same lower bound or not? So this is not known. Is it clear what I meant? Yeah. Okay. Okay, now we can go to the upper bound. So still we have the upper bound that we have for the ordinary powers. And now comes the next, which is a question. If we can somehow, I mean, with this pattern that we went from the ordinary power to square free 1, we can do the same for the upper bound. So as you see, first of all, this is a question. And this is the same to k plus nu, but here minus k. Okay. Do we have this for any meaningful k here or not? For k equal to 1, let us just look at the special cases for the moment. If k is equal to 1, the square free power is the same as the ideal itself. So it means that we are saying that the regularity of edge ideal itself, right, is less than or equal to nu g plus 1, which is the case. You can also check it from what we have for the ordinary power when you put k equal to 1. So there are different proofs for this. So at least for k equal to 1, we had this. And again, let's go to the biggest possible k. When k is just the matching number, what happens? So it means that I'm looking at this, and here what we have is nu 2 times nu g, right? This is also true because we know that Ig to this biggest possible power has has linear quotients. Okay. For those who do not know what is having linear quotients, I just recall here an ideal is said to have linear quotients. Suppose this is generated by u1 to ur. If you can order u1 to ur such that for any I bigger than or equal to 2, you can have some quotients, okay, consecutively, and those quotients are generated in degree 1 by linear forms. And if you start with monomials, then you can say that those quotients are generated by just variables, okay? So just to make it more precise here, oh, by the way, this should be minimally generated. Okay, so here, then you have u1 to ui minus 1, ui is generated by, I keep myself in the case of monomials, and then here I can write by variables. But if you start with a non-monomial case, you can still have this definition, but then these quotients should be generated by linear forms. Okay, so this is the definition of linear quotients. Okay, that you can order the minimal generators so that for any I from 2 on, these quotient ideals are generated by variables. Okay. But how it is related to our discussion? Okay, this ideal has linear quotients. What can it do with the regularity? There is a result which says that if I has linear quotients and it is generated in the same degree, it's equigenerated actually, then it has a linear resolution. Okay, so let us see where we are. We were looking at this power. We said that this power has linear quotients with this meaning. And we said that if additionally we know that our ideal is generated in the same degree, all minimal generators have the same degree, which is the case for us, because this ideal is generated in which degree? The elements of IG are all of degree 2, right? And if you take this specific power, it means that the elements are of degree 2 times mu, right? We agree? Because we are just multiplying those elements. Yeah. Okay. Anyhow, it is generated in the same degree, and it means that it has a linear resolution. So far we know that this has a linear resolution.
We did this same, where we put the IH to the reduced number.
Yes,
What about, we used the fact that it was matching to get the regular sequence, right?
to get the regular sequence, yes.
Yeah,
But now I don't mind how the generators are related to each other. This I don't mind. I just want to know the degree of the generators. Okay, so for an ideal which is generated by, for example, x1, x2, x1, x3, x2, x3, let's say, yeah, I'm taking the power, okay? Maybe it's not a good idea to have this x3, x4. I want to take the second power here, right? Just a simple example. So for a square free power, I can take this and multiply it with this, right? And this is the only possibility. So the second square free power would be x1, x2, x3, x4. The multiplication. It is generated in degree 2. This is generated in 2 times 2, right? And you don't mind if they are all matching, if they are not. You extract the matching from inside, you put as the generators here. If I have 2 here, you take 2 matchings. If I have k here, you take the k matching, right? And then you are just multiplying them together. So of course you are multiplying by k. Yeah, the degree. Is it clear?
yes, but to do this in practice, we have to find the maximum.
You mean the exercise that I gave you? Sorry?
I mean, to find IG to this power, we have to find a maximum matching.
In this specific case, yes, because I'm taking the new power. Yeah, sure. Yes. For example, for this example, if you look at it as an edge ideal of a graph, for that graph, for sure, the maximum matching is 2. Okay. So far, we deduced that this ideal has linear resolution. If you remember yesterday when I explained the structure of resolution, I told you that some special types of these resolutions have their own names. And linear was the case that when you start, for example, with s minus 2 here, then you have s minus 3, and so on. You just increase by 1 each degree, okay? So, but here in the very first step, this ideal, just now we discussed that it has degree 2 nu, right? With some rank, I don't mind for the moment. And then it will be minus 2 nu minus 1 because I'm increasing by 1 and so on, okay? So the shape of this, the resolution of this ideal would be something like that, okay? And we are interested in regularity actually. And regularity was the maximum of the subtraction of the 2 indices. And here, I mean, it doesn't matter if I look at that difference in the very first step or in between or at the end, because we are increasing both indices, the homological degree and the shift degree by 1 in each step, right? Here is the 0 step and the degree is 2 nu. So beta 0 to nu is given here. Here beta 1 and 2 nu plus 1 is given here and so on. And you see the difference of these two guys in each step is the same, right? So it doesn't matter if I look at in which step, so I take the simplest place and the difference here is just 2 nu. So Not only in this case, not only this is an upper bound, but it is the exact value of the regularity. Right? So at least in these two cases, the answer is yes. And we are interested in all other case. Okay? So it's reasonable to start with k equal to 2. So to continue discussion, we want to consider k equal to 2, which is not maybe as easy as these cases. Okay, so far it's clear. Yeah.
There is small confusion when
Can you just talk it louder?
there is a small confusion when you define the square root power. Even the product of those generators who form this regular sequence are generated by the generator. Because in the definition, I noted it's like either U1 or U2 generated by those generators who form the regular sequence.
From the generators.
That means the degree will be 2 for the power that
You multiply them, so you are increasing the degree. So you take the kth power and the generators will have degree 2k.
That means now this division, like the power square root power ideal, is generated by the product of those generators who form the regular sequence.
Who form the regular sequence. They come from the generators of the original ideal. They form a regular sequence. You multiply them and you get the generators of the new ideal. Okay. Okay. So to start this story, I just would like to give you several lemmata to have our tools to deduce that the answer for this k is also yes, and start with lemma 1, which is a very well-known lemma, but anyhow I write it here. Let I be a monomial ideal and U a monomial of degree C, then so we know that the regularity of A is less than or equal to regularity of I colon U plus D, and regularity of I and U, and the second part, regularity of I and X is less than or equal to regularity of I for any variable X.
So then you are choosing the maximum or the minimum from the
Sure. This is the maximum. So this is a very well-known lemma, but I wrote it so that those who have not heard about such tools will be familiar as well. So we will use these two parts to get the answer for k equal to 2. So if I have a monomial ideal and a monomial of degree d, I can compare somehow the regularity of I with the regularity of these two ideals. And also, if I add any variable to my ideal, the regularity would not exceed from the regularity of the original ideal. I mean, again, another exercise for those who are, I mean, it is the first time that are seeing this lemma. We don't want to prove this lemma. One exercise can be just prove this lemma, but I mean, for those who do not have any idea how they are related, I would like to also write this exact sequence that so this is natural map, and here you are multiplying by u. I mean, this is the key actually. So you can first see if it is really an exact sequence, and if you agree that it is an exact sequence, then you can try to understand how we can get these inequalities. Okay, but this is a very important exact sequence for us. We use these two inequalities, but this is our first lemma. But this is a key point actually. We want to use this, the first part, somehow repeatedly to get something about the answer. And it's clear. Then we need to struggle with this colon ideal. So we should manage, and we somehow we need to relate this for our ideal to somehow the square free power. We will see that. I think I don't have enough time now, but we will use this lemma and some other lemmata to prove this inequality for k equal to 2. And yeah, we'll see how far we can go. Thank you.
Are there any questions? Okay. If this is the case, today I think there is a tutorial where you can continue discussion.
Yes, for the tutorial, maybe I just add a few words. I think it's better that I list the questions, exercises that I gave you so far, and maybe some other. And I will split it in different levels for beginners, for those who know something, and research problems. And then I will be around. You can think about them. We can discuss. Some people told me that they want to show me their computation on Cocoa. So I think it is better than people can benefit.
Yeah, in fact, yesterday I have been told by many participants that they are not getting proper time to absorb the ideas. So particularly, please take this opportunity, particularly the tutorial time, to absorb keywords and basic definition. And if you have any confusion, you can. So this is the sole purpose of the tutorial. So thank you, Sara. Thank you very much. There are two announcements today. Okay. So one announcement is today. This is the last day of Professor Thomas Kale here. So from tonight, they depart to Karachi. So you can see him on screen from tomorrow, and he will lectures from the date of from the next 2 days. And therefore, there's a short ceremony which we have scheduled before the lunch. So please be here, be a part of that small ceremony. It's a kind of sharing souvenirs as a token of thanks to the speaker. This is the first thing. The second thing is before before the tutorial of which is scheduled, we have a short 5 minutes. We need 5 to 10 minutes, and I want all the people who are here in this room. We basically Rizwan Jahangir, he recently graduated from Sabachi University. He introduced himself in the great intro. Uh, Rizwan, along with Nams, he introduced a new initiative which is about DRP, and Rizwan would like to explain the idea. And this is something, this is called directed reading projects to promote undergrad research. And the sole purpose of this particular short presentation is to give you an idea, and I think everyone can take a part of this particular activity. So to foster undergraduate research. So basically, this is his idea. This time we'll provide it in the platform now. Start this TRP, and I think we need good connectivity to make it a success factor. So this one require 5 to 10 minutes today at 4 p.m. So these are the two important ones. But now you can enjoy your tea.